Hi, my name is Nicolas, programmer at Tales. I'm happy to do this video to talk about the game architecture of The Last Night, and more especially how we try to empower designers to create a small, dense, simulated open world. Some of you may have heard about the project following a trailer presented during the E3 2017. As of today, the game is still in production, we are a small team, and we are led by a strong vision. An artistic direction. Of course, that's what stands out the most in the trailer. Mixing 2D pixel art and 3D cinematography with state-of-the-art volumetric lighting, dynamic weather, and more. But The Last Night is not only about graphics, it's also a game design direction to deliver an immersive narrative experience in a small and dense open world. Wake up, explore, discover places and events, eat and drink, meet, talk, make choices. A set of characters and situations designed to explore various aspects of a potential future of our civilization, showing where it succeeds and where it fails without judgment. This to incite the player to think about what the future could look like, and maybe think about some philosophical or ethical questions. And to bring this to life, we needed a technical direction. We wanted everything to be animated, dynamic, simulated, and reactive. The weather system, for example, rain, wind, fog, thunder, all of that is defined by variables. In other words, values changing over time. And many elements in the game have to react to those values. Environment can become wet, wind can create ripples on the water, sounds of the rain, or even characters taking out their umbrellas. So how do we tackle this challenge? Can we create an evolving, interconnected, dense open world, but without AAA firepower? In Unity, which is unfortunately not well known for facilitating open world creation, in a completely new visual style, and seamlessly mixing systemic simulation with uncrafted situations. So for the story back in 2017, around the time of the E3 trailer, Tim Soret, the creator of The Last Night, was struggling with the game architecture. They tried different solutions, including things like dependency injection, but it wasn't really satisfying because they really wanted something flexible, easy to use, that would allow the whole team to create the game directly, the logic, the contents, not only the programmers who ideally should focus on creating the core features, systems, etc. A solution that would require as less as possible technical knowledge. So when I joined the team, that was my main objective, to put the whole architecture in place. So what did we end up with? The initial inspiration for the architecture I'm gonna showcase was a famous unit talk by Ryan Hippel, where he explained how to take advantage of Unity scriptable objects to create a powerful game architecture. If you are not familiar with Unity, scriptable objects are assets, files, which are living inside your Unity project. It's a really powerful feature because those scriptable objects are accessible from anywhere in the project, from any scene, from any prefab. So we took that and tried to push it further to adapt the concepts to our needs. I also want to mention that what I'm gonna showcase is part of years of research and development. It's only a portion of what I worked on, among other things, including world streaming, gameplay, dialogue system, AI, etc. And as any solution or tool, it's absolutely not a perfect fit for any game. But it was what we needed, what we wanted for The Last Night, again, to fulfill the vision. The first step was to create a variable system with the objective of having a high flexibility architecture. Usually, programmers are those creating the variables in the code, in the scripts, and then the designers can modify the values of those predefined variables in the Unity editor, in the inspector. Let's take a basic example. You want to define the volume of a sound based on the rain intensity. It could be the sound of rain droplets impacting the ground. So you want to link the rain intensity to the audio volume. No rain, no sound. To do that, you need to know how much it's raining and which audio source you want to affect the volume. The script could look like this. You have to reference the weather system to get the rain intensity, the rain amount, and you have to reference which audio source you want to modify the volume. Then in an update call, so every frame you can inject the rain amount value into the volume of your audio source. In the Unity inspector, you would be able to reference the weather system and the target audio source component. But now you have a direct dependency between your audio source and your weather system. If the weather system is in another scene, there is a problem because, as you may know, Unity doesn't support cross-scene references. And what if instead you want to define the volume using the wind speed? You need to modify the code or to create another script. So you have a high dependency architecture with low flexibility. And if you continue like that, the problem keeps growing. Every piece of code depends on the others. Nothing works in isolation. It's hard to debug. This is not a scalable approach, and it can be a nightmare, a spaghetti nightmare. With our variable system, we can avoid some limitations. In the code, we can use variables without having to define from where the value is coming. For example, we just say, okay, I need a number value, what we call a float reference, and the code is using this value to do something. In our case, setting the audio source volume. Then, we are taking advantage of the Unity editor to define the variable in the inspector. The value can be defined locally as if it was a basic float variable, or using a component variable, a variable you create in the scene by adding a component on a game object, and this component variable can be referenced by any element in that scene, or using a scriptable object variable. For example, the weather system variables are scriptable object variables because we need those values to be accessible from anywhere in the game. We need elements anywhere in the game to be able to know the value of the rain intensity, for example. So now that the audio volume of the element is defined using a float input value, we have low dependency and high flexibility. You want to define the volume using wind speed, drag and drop the proper variable on the field. That's all. In other words, with this system, the dependencies are no longer defined in the code, but in the editor, in the inspector, which is much more flexible and much more accessible, no coding involved. Even better, any team member is able to create and use new variables. But we can go one step further, introducing what I call modifiers. Modifiers are an easy way to modify a value into something else using predefined configurations. In the slide, you can see all the existing modifiers for float variables. There are quite a few. It can be the result of a float operation, a random value, mathematical values like Perlin noise, sinus, p constant, etc. We can also get a value from a specific component, a light for example. So as you can see, using the float from light modifier, we can get the light intensity and inject it into our audio source volume. And those modifiers are very, very powerful because they can be combined. So for example, with a modifier we can get the exposition of a transform. And this transform is itself a variable reference, a transform reference. So it can be defined as a local value, or the value could come from a transform component variable, or even a transform scriptable variable. But it could also be defined using another modifier to return, the player transform or the main camera transform. And that's how you can inject the exposition of the main camera into the audio source volume. Of course, that example doesn't make really sense, but that's just to show you how much flexible it can be. The more modifiers we create in code, the more possibilities we have. It's exponential. That's great, but again, let's take it a step further by making a script even more flexible. Now that we have modifiers, why would we limit our code to set only an audio source volume? Instead, it could just set a target float value, so another float reference, and we let the designers define what exactly in the inspector. In the end, we inject an input float value into a target float value, and we let the designers be creative with it. From that, using the proper modifiers, we can fall back to our previous example and define the audio source volume using the rain intensity value. For the input, we use the current rain float scriptable variable, and for the target value, we use the float from audio source modifier to modify the volume of an audio source. But now it can also do something totally different, like, I don't know, a light with a random intensity over time. Why not? So there, using a random float modifier, we can get a random value as the input, and using the float from light modifier, we can modify the intensity of light. There are many possibilities, and that with a script of only 10 lines of code. With that, you've seen the core principles behind the variable architecture. And on top of that, we have several additional features. I'm just going to show a few very quickly. As you have seen with the float reference example, we have a class to encapsulate the concept of variables. This contains logic to support features we have seen, like the different types of variables, modifiers, and more. Variables also have propagation change notifications. Code, logic, can listen a variable and be notified when its value has changed. For our simulated open world, this is something we are using a lot. It's also a way to lean towards reactive programming by having value changes considered as events. If we look back at our script example, we can modify it a bit, so the logic is executed not every frames, but only when the input value has changed. It can also simplify the code, avoiding to manually compare the previous value with the current value to detect changes. And it's also useful in terms of optimization to avoid executing code each frame when it's not needed. We have blackboards, which basically represent a set of variables to keep things well organized. And we have cross-scene variables, something which is not supported initially by Unity. We can use that when we want a variable to be exposed to multiple scenes without having to create a scriptable object. Because yes, scriptable objects, like everything, have some limitations. The way it's loaded in memory, issues related to addressables or when used inside prefab instances, and we really wanted to avoid handling with thousands of scriptable object files in the project. Our saving system is also taking advantage of those variables. I won't talk about all the details, but to save the current state of a game, the simulation state, we simply save variables values. If you have, let's say, 100 buildings in your world, which can open or close based on some conditions, let's keep it simple and say that they are all opening or closing based on the time of the day. Instead of saving the state of each building, we just save the value of the time variable. And when we load the game, the time value is loaded and we let each building to update its own simulation state based on the new value. With a simple dropdown, we can choose if a variable should be saved. It can be saved in the global game settings for things like graphic settings, resolution, etc., or in the current game save slot. So in the end, it means that any team member is able to create a new variable and make its value written in the game saves. Again, really flexible, really powerful. So now that we have this variable system, what's the next step? It's very powerful for value bindings to connect things, but how do you handle more complex situations with conditional or branching logic? Even if the last night happens in an open world simulation, the experience doesn't rely on systemic gameplay, in the sense that we manually script many interesting things inside that simulation to stage the narrative. We needed a system that is easy to use for the whole team to script various behaviors without coding. In other words, a visual scripting system. Allowing artists, writers, or even sound designers to manipulate or define scripted logic can be really useful. because they can directly inject their personal sensitivities, their expertise. And so I created our own visual scripting system. In this slide, I'm showing how to reproduce the same logic as we saw before, injecting the rain intensity value into an audio source volume. I'm creating a logic graph in the scene. I add an event node to define when the logic should be executed. In my case, when the rain intensity value has changed. And with a second node, I set the new rain value into the audio source volume. This second node is the equivalent of the script we saw before. It takes an input float value and inject that value into a target float value. So again, using the proper modifier, the float from audio source modifier, we can modify the volume of an audio source. You can see that even with a simple example like this one, the visual scripting system is taking advantage of the variable architecture, of the variable propagation changes, and of the modifiers. Of course, we could have used an existing visual scripting solution. At that time, there was bought a famous visual scripting plugin for Unity, which has been acquired by Unity in 2020 and is now integrated for free in the editor under the name of Unity Visual Scripting. So first, it wasn't the case when I started creating the whole game architecture. Besides, we also really wanted something tailored to our needs, something that would take advantage of our variable system, a solution on which we would have full control. Visually, Unity Visual Scripting is pretty, but I think it has some big issues. In terms of usability, again, let's take a basic example. If you want to simply increment a float variable when you press space on your keyboard, it already takes 4 nodes just to do that. With our system, it's only 2 nodes. It's well known that the more you have nodes in your graph, the harder it is to read and understand what's happening. So I let you imagine the difference it can make when you have big complex graphs with dozens of nodes. More than that, with our solution, the logic is also more explicit, in my opinion. Just by reading the titles of the nodes, I can understand what's happening. On keyboard space up, increment my variable by 1. It's pretty straightforward. On the Unity Visual Scripting side, you have more back and forth in terms of reading the logic. Of course, Unity Visual Scripting also have its own variable system, but less powerful. No modifiers, no propagation changes, etc. But the thing is that variables are referenced by names using weak string references, which is crazy. Because as soon as you rename a variable, you break all the existing references to it. This is something which I think, for a project as complex as The Last Night, is totally not acceptable, too much dangerous. You know that creating game is already very difficult, so we don't need to add such dangerous behaviors in our production pipeline. No way. It's also interesting to compare performances. If we take the logic from the previous slide, incrementing a float, and we execute it 100,000 times, what results do we get? First, with C# code, we get something around 10 milliseconds of processing. Important precision, it's not incrementing a simple float, but a float component variable to make the test equivalent to what we do in visual scripting. There is of course no memory allocation. Now, with Unity Visual Scripting, we are close to 700 milliseconds. This is 70 times slower than C#. More than that, the memory allocation is significant, with 11 megabytes. If your game is running at 60 frames per second and you have such logic executed every frame, it will be executed 100,000 times in 28 minutes. So you would have 11 megabytes of allocation every 30 minutes. Okay, but again, it's a really basic logic, something very common, incrementing a float value. You could easily have something like that on a prefab, which could be instanced 100 times in your scene. And in that situation, this is no longer 11 megabytes of allocation you get, but 1 gigabyte every 30 minutes. This can, of course, put a lot of pressure on the garbage collector. What about our solution? we have almost 50 milliseconds of processing. So it's 5 times slower than C#, but 14 times faster than Unity Visual Scripting. That's the result of using interfaces instead of reflection. Because yes, Unity Visual Scripting, like all the visual scripting plugins for Unity I've seen so far, is using reflection a lot, which is bad for performances and memory allocations. The advantage is that Unity Visual Scripting is automatically compatible with the whole code base of any user. In our case, we preferred to have control on what is exposed to the visual scripting architecture. We have tools to make it easy to create new types of nodes, but it still requires some manual setup. That being said, we also have some nodes that takes advantage of reflection to get set fields or call methods using reflection. Those nodes are for temporary uses and are here to ensure that a designer never gets stuck waiting for a new node to be implemented. And regarding memory allocation in our solution, all potential memory allocations are cached and reused. So on the long run, we have zero memory allocation. Of course, keep in mind that these numbers can change depending on the logic created, but I think it should be safe to say that our solution is at least 6 or 7 times faster than Unity Visual Scripting. And again, more than performances, the difference in terms of memory allocation is huge. So for all those reasons, performances and what I mentioned in the previous slide, and knowing that we would use visual scripting a lot for our open world, creating our own visual scripting system was sure a big investment, but I think in the long run it was worth it. Of course, we are not doing everything with visual scripting. Code is used to create core general systems in a way that is reliable and performant, sometimes using C# jobs on burst when it's relevant. It includes player controls, crowd behaviors, pathfinding, etc. On its side, the visual scripting is used to define things on a case-by-case basis. It can be value bindings as we saw before, or the interactions, what happens when you interact with this element, triggers, etc. So we have systemic features versus handcrafted elements. That being said, as you know, with great power comes great responsibility. So we still need to be careful to avoid things becoming out of control, with tons of variables and connections in all the directions. Of course, we try to avoid that, first by not using visual scripting for everything. And as in code in the end, we need to educate ourselves to use the best practices and keep things organized. The same way that in code you try to minimize scopes of variables, you don't want to use only public static variables. Here it's the same. We don't want to use only scriptable object variables, because it would be terrible, really terrible. Okay, we can go further by combining scripts and visual scripting. Let's take a simple example. The doors. We have different types of doors in our city. Sliding doors, rotating doors, manual doors, automatic doors, etc., etc. And each door could potentially open or close based on different conditions or actions happening in the game. So how do we handle that? Everything that is common between all the doors, in other words, what is systemic, can be defined in a door C# script. It could be seen as a door API, and it can potentially handle some features. For example, answering the door is not closing if there is a blocking element inside the area of the door, like a character. But the script would have no idea of when the door should open or close and how it should happen. The when is defined by external logic. It can be related to player actions, entering a code on a keypad, door automatically opening when a character is detected, or even a button in the Unity Inspector for quick and easy debugging. All those triggers could send open or close commands to the door script. And then, on the other side, we define how the door is opening in visual scripting. Animations, sounds, lighting, etc., etc. The door script is able to know when the linked visual scripting logic has finished, to define exactly when the door can be considered as opened or closed. This way, we can have one door script which can be reused for different types of doors and different in-game situations. Again, We try to get the best of both worlds, something reliable and performant, while taking advantage of the flexibility of visual scripting. Concretely, we have a base door prefab with common setup, including the door script. Then, we can have prefabs variants to define the different types of doors. In the example, we have a block-out door with a rotation logic. And we have another prefab variant, which is a double door where the visual scripting logic is triggering an animation played by the Unity animator controller. If needed, we could also customize things per door's instances by overriding prefab values directly in the scene. Usually, we add on the prefab a blackboard to expose settings that are likely to be modified on a case-by-case basis. In this case, it could be the rotation duration, for example. This allows to easily customize each door instances directly in the scenes without having to dig inside visual scripting logic, avoiding the risk of getting lost in the implementation details. That's a basic example, showcasing how we can mix code and visual scripting. To finish, as I did for the variable system, I'm gonna show a few additional features. We can create visual scripting logic directly inside Unity animator controller states. Something useful when you want to create more complex animation logic. Of course, we also have some debugging tools. And if I had to mention only one, it would be the variable monitoring system. Using this tool, we can track values changes over time, and more importantly, to know what changed a value. So by clicking on the curve, I can know what change has happened, what was the previous value, what is the new value, and what caused the change. Is it from the inspector, from another script, and if so, which instance of this script, or maybe from a specific visual scripting graph, which node, etc. Very useful. To conclude, we basically moved value bindings and contents logic from code to editor. We try to decouple things and have things more flexible, more modular. Programmers should focus on implementing features, systems, not the contents. Of course, I've spent a lot of time creating this whole architecture, but I'm speaking globally in the long run. We give more power to the designers. We have faster iterations. It's easier to modify a visual scripting element than modifying a script, especially when after each code modification, you have to wait something like 20 seconds due to the compilation and assembly reload. Changes made in visual scripting are applied instantly. We can also open any visual scripting graph, right-click on any node, and select Execute in the contextual menu to directly trigger the logic. It's very useful for quick testing and for debugging. In the same way, we can right-click on any node and enable debug options to add console messages or even pause the game each time a specific node is executed. All of that is making debugging easier. And that's the end of this presentation. I hope you liked it. If you want to follow the progress of a game, you can have a look at our website. Or even better, you can join our Discord server. There are quite a few active members with really interesting discussions related to games, but also cyberpunk, cinema, or even photography. So don't hesitate to have a look. Thank you.